Now let's see, once the eigenvalues have been determined, how can we use those eigenvalues to compute the eigenvectors for the transformation matrix. Now, previously we had this equation which is 2 minus lambda 2, 0, 1 minus lambda in a matrix multiplied by vector is equal to 0 vector. Now, what we can do is we can start substituting the specific values of lambda in this equation to find out the corresponding eigenvectors that are associated with those eigenvalues. So, for example, if I take lambda 1 equal to 1, which is an eigenvalue that we have found out, let's see how we can use this along with this equation to find out the vectors that will correspond to lambda 1. So, the first thing that we need to do is we need to substitute this value of lambda in the overall equation that we have. So, if you do that, this will become 2 minus 1 and 1 minus 1, and if you simplify this, this matrix will become 1, 2, 0, 0, v multiplied by 0. Now, here if you look into this equation is essentially two equations together. So, what we can do is from here we can essentially derive this following two equations. Now, how we are doing that? So, let's take this v, right, and let's assume that this v vector is denoted by something like this, where v1 comma x, v1 comma y are the two elements in this vector, where 1 is corresponding to the eigenvalue, which is lambda 1, and x is the first component and y is the second component. If v is like this, then I can have this v here, and then I can multiply 1 times vx plus 2 times vy, and that will give me the first equation. Similarly, 0 times v1x plus 0 times v1y is equal to 0 is the second equation that we can get from this equation that we have. Now, we can solve this equation. So, one of the things that we can do is, we can simplify this equation, right, and we can write that v1x is equal to minus 2 v1y, right. And if that's the case, what we can do is we can quickly find out solution, because there are a lot of values that will be satisfying this. So, from here what we can do by using the substitution, which is basically by substituting v1y equal to 1, and if I substitute that, that will give me v1x equal to minus t. So, from there we can determine one of the eigenvectors that are associated with the lambda 1 equal to 1 eigenvalue that we have, right. So, this is the process how we can take eigenvalues and then create a system of equation and then find out the specific solution to that system equation to find out exactly the eigenvectors that will be associated with this eigenvalue. Now, we can take the same approach with also the second eigenvalues that we have identified for this transformation matrix M, and see how we can come up with a eigenvector that is associated with the second eigenvalue of this transformation matrix. So, let's carry on the same process, right. So, this is the eigenvector for lambda 1, but let's see how do we find out the eigenvector for lambda 2. Right, the same equation right here. What we'll do is, in place of lambdas, we will substitute this value lambda 2 equal to 2, and from there we will essentially simplify, which will get this equation, and from there we will simplify and we'll get this equation. Okay. Now, similar to this two equation, this will also lead to two corresponding equation, and you can check with your notice. You can basically do assume that the first component of v is v1x and the second component of v is v1y, and from there you can find these two equations that are out there. Now, what is the way to solve this equation, right? We need to, in order for this equation to be valid, one of the things that needs to happen is that the v1y has to be 0, and then that will lead to multiple different values that you can select for v1x. So, if you just heuristically or by guess we pick up 1, this will correspond to v2 equal to 1, 0. Okay. So, again here in both the cases we are basically using guesses, and that is helping us in finding out the actual values that satisfies this equation. So, one thing to note for this set of equation, that this will be only satisfied if these both will be only satisfied if v1y is equal to 0. And then any value of v1x is going to satisfy this. Okay, so we will take the first, just one, which is like the most intuitive guess that we can take, and that will be the solution. We could have also taken something like this, right, where the v1 is 2, 0, and that would have also been a solution to this equation. So this would also have been an eigenvector. So you can see with a single eigenvalues, you can have the multiple one. But if you carefully look into this, the span of both these vectors are essentially the same. Okay, so we take the simplest one. And in this case, we will say that rather than this one, we will basically select this one as an eigenvector corresponding to lambda 2. So this is how you can take basically a transformation matrix and go through series of steps. First, determining the determinant, which is basically the characteristic equation. From the characteristic equation, you find out the roots of that equation, and that leads to different values, eigenvalues. And corresponding to each eigenvalues, then we again go back and solve that, and we find out the corresponding eigenvector. So this is the numerical process of basically finding out eigenvalues and the eigenvectors corresponding to any given transformation matrix that might be there. So let's move on, and let's also discuss some other important concepts which we need to know with respect to eigenvectors and eigenvalues. The first is like it is not necessary to have eigenvectors for every linear transformation. Okay, so it is not necessary that we will have eigenvectors. For instance, in some cases, the transformation matrix will be essentially doing some sort of rotation. So whatever you pass on, whatever vector you pass on, it will rotate that vector. Okay, so in those cases, we will never be able to find the eigenvector for that transformation. And typically in those cases, the eigenvalues are essentially complex number. Remember, when we solved, this eigenvalue determination through this characteristic equation that we have right here, this equation, in many cases, this quadratic equation might have complex solution. You might not have any, non-complex solution. So if the solution or the lambda is a complex number, then in that case we will not have essentially, we will be essentially having a rotation matrix or a type of rotation matrix, and in that case there will be no eigen values or there will be no eigenvectors that will be associated with that that type of transformation. Okay. Now, the negative eigenvalue shows that the vector is flipped but still staying in this span. Okay, so if you have a negative eigenvector, right, and it is in original direction, it's going to be on the same span, but it's essentially flipping, right? But it's essentially the direction is not changing. So this is the meaning of negative eigenvalues when you see eigenvalues, negative eigenvalues when you're with respect to given transformation matrix. And as I already alluded, towards the end of the previous slide, that single eigenvalues can have multiple lines of full eigenvectors. For example, if you go back here, this vector was 1, 0, but I can also, as I mentioned, I can have a vector v2 which is equal to 2, 0. That will be also eigenvector. So in that scenario, we can say that single eigenvalues can have multiple lines of full eigenvectors. And what we are doing, for example, we are scaling everything by the same value. And if you are doing that, then we will be always lying in the same span, right? So summarizing, eigenvalues can have multiple lines of eigenvectors associated with them. So with that, let's also discuss some of the common terms that you might hear or come across with respect to eigenvectors and eigenvalues, and it's important for us to also know those common terms. Okay, so here are some of the terminologies that typically the set of all eigenvectors corresponding to eigenvalues together with 0 forms a vector space called eigenspace. This determinant, which we used to basically equate to 0 and find out the values of lambda or the values of eigenvalues, is known as characteristics determinant. And this equation, when we equate it equal to 0, that is called characteristic equation. Some other things, that eigenvalues are called as characteristic values. So you solve characteristic equation, and you essentially the output of that characteristic equation is the value of lambda, and that's why eigenvalues are also known as characteristic value. The set of eigenvectors that are associated, that you find out, all of them combined together is known as spectrum of the transformation matrix. And The largest of the absolute values of the eigenvalues is called the spectral radius. Recall in the previous problem when we were solving, there were two, eigenvalues. Lambda 1 was equal to 1, lambda 2 was equal to 2. So in this case, this was the maximum absolute value that we can get, and that will be called the spectral radius of the transformation matrix for our example problem. So I hope you understood some of the basic concept, at least the geometric intuition behind what is happening when we are trying to find out eigenvalues and eigenvectors of a given transformation. Then also we discussed like how to compute them numerically. There is a process. We first of all come up to the characteristic equation. We solve the characteristic equation. We find out the lambda. And then we use that to go further and find out the corresponding eigenvectors. Okay. So with that, we come to the end and conclusion of this lecture, and we will come back again and talk more about different things. Thank you.